Make sure this. Thanks. Just a few things starting out. So what is Boomer? Boomer's, well, John already mentioned it's the new subsystem. Solaris has had audio for a long time, but we haven't had very good audio. So Boomer is basically a modernization of audio for Solaris, and that brings in a number of things, but among them surround sound, some high-resolution, high-definition audio. Those numbers are interesting if you're interested in audio, but probably not otherwise. And the whole thing, there's a lot of different audio subsystems out there in the free and open source world. But Boomer is primarily a kernel audio subsystem. There are a couple pieces in userland, but mostly they're things like control utilities. The whole thing is, of course, open source, which is new for Solaris Audio. There was a number of drivers up before this that were in user closed. Those drivers were rewritten for Boomer. So, you know, if you have questions about anything I say, or if you want to find where I'm making mistakes, you can go use the source and tell me I'm wrong. Boomer's also compatible. It has to be compatible because of Solaris's application compatibility guarantees. And there's some API requirements that come out of that are significant. And we'll talk about those more. That's with that Audio 7i. And in this presentation, you'll see a lot of places where I put in parentheses a number and maybe a subsequent letter. If you haven't seen those before, those are man page references. So you can just say man space dash s 7i space audio. But we also had to have full support for legacy devices. There were quite a few of them. That was interesting. That blanked up here too. I apologize for that. I guess power management is doing it the right thing. It has to be efficient. A lot of things, a lot of history with some of these audio devices that were out there was that, gee, when I start running this audio application, the system gets slower, or I can't run very many audio applications. And it also means it has to be scalable. When you consider a Sunray server, Sunray servers have to do audio processing, and we're going to talk more about Sunray at the end of this presentation. But you can have literally hundreds or even potentially thousands of DTUs. Those are the actual Sunray units. They stand for, I think it's data terminal unit or something like that. When you add it all up, you can have quite a number of audio applications. So it has to be scalable and performant. Some things that we don't have in Boomer, MIDI support, and that actually means that we don't support hardware wavetable synthesizers. And we don't have support for external MIDI connections. So you won't be able to plug in your MIDI keyboard. And, well, you can plug it in, but it's not going to do anything very interesting, at least not because of Boomer. You could conceivably, or someone else could conceivably contribute a project to provide a MIDI framework, and that could sit alongside Boomer quite compatibly. But there's no necessarily intrinsic reason why those two pieces necessarily have to go together, despite the historic reasons of having it in places that way in Linux and other operating systems. Boomer's also not a porting layer. There are other open source audio frameworks that try to make the effort to make it easy, and I apologize for that word effort. It's supposed to be effort. They try to make it easy to take to take drivers from one place to another very easily. We didn't do that, and we'll talk more about that. We also are focused primarily on consumer audio and desktop audio applications. You know, if you want to run your radio station or be a recording studio, well, if you're able to do that on Solaris, if you've ever been able to do it on Solaris, or even if you're able to do it on Linux, more power to you. We chose not to try to solve those problems. We actually think that most people are using other platforms for that. And for the same reason, we don't do any of the high-end digital signal processing services. If you want to use audio, the audio framework, to try to get really high-resolution signal processing, you're going to be disappointed by the latencies associated with a normal time-sharing operating system. And there are some audio frameworks that try to solve that problem. Boomer doesn't. So where were we before audio, before Boomer? Solaris had a very complex streams-driven framework. It's actually a second generation framework for Solaris. I won't even mention the first generation. But there was it was a maze of code, and a lot of it was actually dead. It had support for features that had never been used or tested. And despite all that, it didn't support the things that people did want, which is, consumer audio has really advanced since 1985. We're now at the point where people want to use surround sound. They want to do higher resolution audio, and they have a variety of interconnections. And even now on laptops, you find that you've got people that can do some of this high definition audio. They've got multiple jacks on here, and sometimes the jacks you want to be able to reuse a jack. So this could be a microphone, but what if I wanted to hook up a rear set of speakers? Well, I only have two or three jacks. That means I need to be able to reuse a jack. So all of that stuff is supported through Boomer. It looks like when I was waking this up, it went forward. Is that okay? So that's okay. So one of the things that I think I missed on the previous slide is that Boomer is made up of some components that are licensed from Forefront. So we want to talk a little bit about Forefront Open Sound System, which prior to Boomer, if you were to run Open Sound System on Solaris, you could get this download for free. You could also pay for it. And there's some good things, and let's talk about the good things there. It was free and commercial both, and you can get it on a number of different operating systems, a number of different licenses. But the best thing probably about Open Sound System, which may also be the worst thing about it, is that it has a very popular API. So this makes it easy for applications written to one API to work across multiple operating systems, as long as those operating systems also support this API. The other thing it has is support for a lot of devices, just a huge variety of devices. Wake up, wake up. It also has support for a lot of features on those devices, and we support some of those features, but not all of them, and we'll talk more about that. And this extensible mixer API that I'll get into. But there's some things about Forefront's OSS that, at least for Solaris, we thought were not necessarily the best. I think I used a different word up there. The lack of native support. Basically, Forefront's portability goals were designed so that you can port to everywhere, and this forces you to take a least common denominator approach. And you leave out some things on the features on the floor that you really want to have in the sound system that you're going to ship with your operating system. Support for advanced interrupts, MSI, MSIX, suspend, resume, device quiesce. And actually, the emulation that they had, there was some for the legacy Sun Audio stack, was not very good. And for us at Sun, it's very important that all these legacy applications continue to work. So we had to have a very good emulation. There was also a number of scalability limitations in the stack, which limited where it could go without major work. The scalability concerns were a major one, and there was some performance concerns. A lot of people, I don't know a lot of people, but some people have complained that with these performance things, and if you actually go through the code, as I did, you find that there's actually quite a number of divisions which are very expensive in terms of CPU cycles on very hot code paths. You had multiple divides happening for each audio sample, and that's one of the things that in Boomer we've tried, and I think we've been fairly successful at eliminating and replacing with better alternatives. One of the other detractors here was that there was a lot of work required in a device driver to interact and supply the services to the operating system, and I just felt that device drivers should have less code in them rather than more code. And actually, a good rationale for that would be that last presentation with Parfait that demonstrated where all this code is. Having less code in the device drivers and more code in a shared bit of common code reduces the likelihood of having all those kinds of bugs that we want to avoid. I'm not really going to touch on the separate vmix and remux drivers, other than to say that it adds another level of complexity, and if you use them in Forefront, they're a performance limiter. Not a huge one. So with Boomer, what we did is we have this old code from Sun and we have old code from Forefront, and neither one of them is exactly what we want. So we cherry-picked the best bits. And there were some really spectacularly good bits. There was also some pretty spectacularly bad bits. We picked the good bits, left the bad bits, and rewrote the rest. And the end result here is Boomer. The best bits probably from Forefront, the GRC3 sample rate converter, which I'll talk more about. The best bits from Sun, there was some conversion support for ULaw and ALaw that was superior to anything anybody else has. There was some good volume limiting code from OSS. And then almost all of the mixing code and the DDI stuff and the glue that puts it all together, as well as the API code, we wrote from scratch, because frankly both audio subsystems were crap in that regard. Pardon my language, but spade's a spade. We also replaced the GStreamer module. I say improved, rewrote a lot of the module. Forefront had paid a contractor to do some work on it. It's a module that's in the GStreamer ugly, not ugly bad. The bad module, if you know of GStreamer parlance, we've significantly improved it. And there's the gratuitous screenshot for it. Woohoo! One of the things you can't see on the screenshot, and I didn't bother to make separate snapshots, is if you clicked on the options tab, you would see that for this particular screenshot, which was taken on a Sun Ultra 20, actually an older system, you can actually get jack retasking, and even though it has only 3 jacks out, you can now get with Boomer 5.1 audio support on this system that never has had it before, at least not under Solaris. So, woohoo. Let's see. Just looking here about APIs, there's a whole lot of information here about all these APIs, and I can spend a lot of time talking about all this. I'm kind of thinking that we don't have as much time. 45 minutes turns out not to be very much time. I've already pruned a lot. The good news is that all this stuff is both in the slides, and there's also a separate paper that I wrote for the proceedings that has a lot of detail in it. So if you're interested more in that, I would encourage you. But the issue here, the biggest issue here, is that the Sun Audio API was based on streams, and that creates a number of unique considerations. This is what this slide is basically pointing out is some of the limitations in the legacy Sun Audio that were actually API limitations, and these were API limitations that we really couldn't overcome. So our solution to this is not to overcome them, but simply to limit what applications using this API can do. And we're going to take the approach moving forward that we want applications to use a different API. This is a whole other mess, and I don't have really time to break this one down, but there's information here. People, if you really want to see all the ways that audio applications can get really messed up, look at these slides. They're okay. So the approach we took for Sun Audio was that we would create one virtual device for each process. That one virtual device is actually a very limited device. It gets one soft volume control. By a soft volume control is when that application changes the volume, it only affects that application, and it's done using a software attenuation of the PCM data. And it's just a monophonic value. We don't give access to the stereo values. There's a couple reasons for that, and they really had to do with how, when you deal with volume controls now, not just with this API, but applications using the other API, and you've got an application panel that's going to display per application volumes for a bunch of audio applications. How do you represent this, and how do you deal with representing a stereo value and mapping that to a 7.1 value? And it turns out that for almost everyone who does per application volume control, they just want to be able to adjust the level for that application. to adjust the levels for a surround kind of configuration, that's where you want to adjust the hardware levels, and we'll talk about that in the Mixer API. So we also nuked some API from the audio framework in Solaris that applications weren't using, and that created another bunch of problems, and that you couldn't actually rely on because it turns out that the Sunray audio stack is never supported. And this saved us literally thousands of lines of code. And of course, the good news here is that eventually we hope to mark this whole API obsolete. We probably will never be able to remove it because binary compatibility guarantee, but at least we can get people off of using it in new code. So there must be an alternative if we're going to obsolete the legacy Sun Audio API, and that is we're going to introduce this new, to Solaris anyway, OSS API. It was originally designed for Linux by the folks at Forefront. It was actually probably the first universal audio API for Linux and ultimately then the other free x86 operating systems. And to this day, it is still the only real audio API, at least supported directly by the kernel, for FreeBSD. It's a simple character device interface, has a bunch of IOCTLs, optional mmap support. This last bullet here about being fragment-based is interesting, and I'm going to talk more about that, but this is a strength and a weakness of this API, and that is that it wants to chew things in, chew on audio data in chunks of data that are grouped in what is called a fragment. And the fragment is usually considered to be the amount of audio data that gets processed at one interrupt, in the time of one interrupt. So with a typical audio device, you might be interrupting at, say, 175 hertz. So at a 48 kilohertz, it's going to be that corresponds to a fixed amount of data, and that's what a fragment is. And that notion of a fragment, if you look in the code, it carries through everywhere, and that's one of the reasons why I kind of feel it's important to bring it up here, because it gets expressed all the way up into the DevDSP API. And unfortunately, historically, there was a legacy that the power that these fragment sizes were always a power of 2. There are some devices, some real devices, not just in Boomer but in Linux, that don't use the power of 2. This actually breaks a certain number of applications that incorrectly assume this legacy. Some problems I think I just already hit on that second bullet. Some of the commands in this API are actually really old and should really be obsolete. And in fact, in Boomer, we have a number of them that we either have stubbed out or we support, but we'd have left undocumented because we don't want people to really use them, or there's better ways of doing that. And I guess the rest of the slide is more details about this blocking. That has to do with latency, and we've had some bugs associated with that, both in applications and in the framework. For the most part, it seems to work okay now. Details of the enumeration API. So we separate the enumeration API from the Mixer API, or the Mixer extension API. And this is different than where Forefront OSS and OSS on FreeBSD is today. The enumeration is just what it sounds like. You want to be able to find, if you're an application, you want to be able to find the audio devices and give the user a choice about which audio devices that you want to use. As an example configuration, you could imagine you have a game or a movie playing on the speakers, and you have and those are the outside speakers on your line out, and then you have a USB headset or a headset on a different audio jack to be able to answer a voice over IP call. Intel, in their HD audio specification and in their marketing literature, actually have this idea of being able to extend this to audio zones and a lot of different kinds of things. But at the end of the day, you want to be able to select what audio devices you use for what purposes, and you need an enumeration API to support that. I'm not going to go into the details of how you use this. If you're interested, read the materials. Forefront OSS conflates the Mixer and the the mixer, or what I like to call the control API with the enumeration API. There's some real problems, some security issues associated with that. If I get time to it here, we'll cover it. If not, the details are in the paper and also on the thing. Here's just a screenshot of what, if you were to have this was actually taken also on an Ultra 20, same Ultra 20, with an add-in CMI 8738 add-in card. So 2 audio devices, this might be what it looks like. And that enumeration API, by the way, is not just via reading file, but there's actually much more structured and programmatic way using IOCTLs to access that. So the mixer API, or the device control API, is the other side, and it gives you access to things like volume and what ports you're going to use for what, and any kind of hardware setting you can possibly imagine. In the OSS land, there was actually an older version of this that was just used numeric bit masks. We don't really support that. We sort of do, but at a much reduced level, and it's more like to access like a soft volume sort of thing. To really control the device and get access to the full richness, you need to use this new 4.x style OSS API that gives you access to free-form names and numeric values. And the values are actually typed. And one of the things is that this API is really only to be used by your desktop mixer applications. So for example, GNOME Volume Control, Mixer Applet 2, or you could have some other application that really is just about, it's like you could imagine a mixer panel, right? To adjust all your levels and what port you're using for what. An application like Real Player or your game or whatever, it doesn't need access to any of this nonsense. So only a few applications really have to be dealt with this. This slide deals with this this problem that I was talking about the security problem. And basically the idea is that in the old days of Forefront, if you wanted to control the volume of, for example, your USB audio, you would open DevMixer and issue an IOCTL using an index number for that USB audio device. If you wanted to change the volume of your onboard audio, you would open DevMixer and issue an IOCTL with the index number of your onboard audio device. The problem here is that in both cases you've opened the same device node, DevMixer, and you've completely circumvented the privilege checks on the device node. So in Boomer, we separate this into 2 separate operations. The first operation, you open DevMixer to find the device, so you're actually using the enumeration API. Then to control the device or manage it, you open the real device node, which you got via the enumeration API. When we pointed this problem out to Forefront, they agreed, and their latest documentation actually recommends that you use this approach as opposed to the way they were doing things previously. So this slide is basically is a picture of how all these pieces in Boomer put together, and for the most part it's accurate. There's been actually, well, it hasn't changed yet, but there's about to be a change, which is this AU stir module up there. This kind of looks like a box. It's a bolt-on. That module is about to be removed, which will be a good thing. At the top, basically, of this diagram, we have user land applications, and there's a couple different kinds. And then you have, in this big bluish box, is essentially the audio module and represents the core of the Boomer, and then the subsystems within that. And then down below, we have the various different driver modules. And you'll note that one of them is actually an AC97 module that's not part of the Boomer core, but it's not really a device driver in its own right either. It's a library, and we'll talk more about that. I'll probably want to come back and forth to this slide as we go on. How am I doing on time? I have about 10 minutes? Okay. I'm not going quick enough. I apologize, guys. So the audio core is basically that big monster module, and it has a lot of different components into it. The API implementations for both OSS and Legacy Sun, and then there's this personality glue. The various conversions for audio. You have to be able to convert sample rates and formats. We'll talk a little bit about that. The mixing itself, the control framework, and this device driver interface. So I already mentioned a little bit about fragments. When you look at the code, or if you look at the materials surrounding all this, you'll see that there's a couple of terms that we use, and this slide basically is trying to clarify those terms. I think I've already said what a fragment is. So what's a sample and what's a frame? A sample is if you have stereo data, at any given point in time, you have two samples. You have a sample on the left side and a sample on the right side. And it could be 8, 16, 32, and eventually, well, pardon me, 8, 16, 24, and eventually 32, at least in Boomer, bits wide. A frame is the channels, each channel has a sample. A frame represents those samples put together. So 7.1 or 5.1 audio has 6 samples in a frame. What people normally call the sample rate in Boomer is really a frame rate. So for example, if you have 48 kilohertz audio, you really have 48,000 frames per second. And a given channel's frame rate is also its sample rate, but that's just for that channel. And then I already mentioned a fragment is a bunch of frames processed together, and it's usually more than 100 frames. The exception for now is USB, which has a ridiculously high interrupt rate, and that's actually a bug that the USB audio guys are working on fixing. So, if you were to look at that picture, there are several different pieces. One of the neat things about Boomer is that we had this idea that we wanted to be able to support multiple different APIs, and we wanted to do it cleanly, and we didn't necessarily know what the future was going to hold. So we built an interface boundary and put the API implementations above that and have a well-defined interface boundary for them to work across. This allows us to easily support the current APIs, the Sun Audio and then the OSS, but maybe someday also or Mac OS's API, or who knows where audio is going to go in the future. So, the client personality interface also provides the entry points, the device driver or CBOps and DevOps, if you remember John's talk, entry points for these personalities, and then ultimately also for the drivers. And each personality can provide overrides on each of those entry points to do whatever it needs to do. This is a description of what one of the things about Boomer is that it's built completely on the concept of an audio buffer, which is basically a FIFO with a whole number of fragments of audio data, and a consume and produce index. So those of you with software engineering backgrounds will understand this. One of the key things that are about this, we use our count head, our produce and consume index are 64-bit counters. They don't wrap, at least not with any sample rate that is in use today or likely to be in use within the next decade or two. They count in frames. They don't count in samples. They don't count in bytes. They don't count in words. If you go and look at the code, if you don't realize that, it will confuse you. But so if you're looking at the code, remember that all these counters, everything that Boomer does where it provides a counter is in frames. And there was a comment there about the index being modular, but ask me if you don't understand it. I've already said that the AU stir module, that module that looked like a bolt-on, was going to be removed. What that module is designed to do is to work around a limitation in the Solaris VDI. Now, that limitation is that you can't have a streams driver and a character driver in the same device driver, that you needed a separate driver. Interestingly enough, earlier this week I fixed it, I removed that limitation, and the way I tested that fix is with an implementation of Boomer that doesn't have this AU stir module. That code is still in code review. Once it gets through code review, I hope to push it, and then we'll eliminate that code. And it'll save about another 1,000, 1,600 lines of code somewhere in there. So I love deleting code. Especially when it's code that I'm ultimately responsible for and will have to support. So anyway, this is just a kind of a blurb on the GRC3 sample rate converter. Now, my opinion on the GRC3 sample rate converter is that it is very good. I consider it to be state of the art. Who here is familiar with FreeBSD's audio subsystem? Anybody? Okay. So FreeBSD has a new sample rate converter which wasn't available when I started this work, called it's the Z Remixer. And the claim is backed by pictures, if you were to look on this on their website, that it is a cleaner sample rate conversion. Now, I've talked to the guys responsible for this, and I'm hearing some conflicting data, and I haven't had time to try them both. But for now, I'm very pleased with the GRC3 sample rate converter. It's proven to be quite excellent as far as audio quality and as far as scalability. I'd still like to take a look at the Z remixer, and that is on my list of potential future work. Okay, I'm going to move ahead then real quickly. This is just a description of what audio mixing is. Hopefully everyone here, if you're interested in audio, you know what audio mixing is. If not, ask me or read the thing. I've skipped everything about the DDI. Actually, I'm going to go up for a second. One of the things I wanted to talk about really quickly here is Boomer's mixer, which I'm quite proud of. I wrote it, so I should be proud of it. But we have found it to be really scalable. I've had literally hundreds of audio applications on a desktop Ultra 20 running simultaneously and smoothly. And to my knowledge, none of the other audio systems that I've been able to try have had that kind of scalability without suffering dropouts and other audio problems. And I attribute that to two things. One is that GRC3 converter that I talked about. And I should have actually said more about that GRC3 converter, because I took the code that was from Forefront, which actually on its own I don't think was quite as good. Mathematically it was very good. But I addressed for Boomer a number of the assumptions that weren't in there. I was able to make some assumptions about sample sizes and remove some variable divides and replace them with bit mask operations. And it makes a huge difference. Those of you who do software optimization will understand that. You definitely want to, whenever you have the chance to avoid a divide, you want to do so. And I was able to remove a number of them from the hot code paths in Boomer. The soft volume gain limiter from Forefront is also extremely good. So, and to the point now where we believe this is good enough that the Boomer, you don't have a choice. You always get software mixing. There's no way to turn it on or off. You don't need to. And we also avoid a separate vMix layer, which is what Forefront uses in their mixing layer as well. And that saves some performance issues. I'm very proud of Boomer's approach to the Remux facility. I believe that's a significant Boomer innovation. There are still some concerns about it. I'm not going to go into it here because I'm out of time. But I would encourage anyone who's interested to look further in the documentation or the paper or the slides. Boomer introduces a new DDI. It's not committed. It's consolidation private for Solaris. And the goals here was to simplify things for device drivers to the point where you could build a driver without being a PhD or a rocket scientist. And in fact, I think we've achieved that. The typical AC97 driver is only about 1,000 lines of code now. And it's pretty easy to port drivers from one platform to the other. And I've gathered enough experience doing this now that I believe that we've been successful there. If you want to actually see the DDI, I don't have time to cover it here. It is in a bunch of material of it is in the paper, but you can also look at this art case, which actually has draft man pages. Again, it's consolidation private. I hope to be able to raise its commitment level later once we get a little bit more background for a little more experience with it. I'm going to skip the audio control framework. I think I already mentioned the AC97 library. So to wrap up, I would like to talk a little bit about where we're going. Sunray Audio, a lot of people have been asking for Sunray Audio. It is our intention to support Sunray Audio, and I've got a whole slide on it after this that I'm going to come back to. Virtualized audio, I'll explain that too. I've got a separate slide for it. The LX audio is just cleanup. mmap support, got another slide on that too, but that's actually going to be pretty easy to do. I'm going to just go ahead and move on to the next slide because I feel like I'm too many forward references. So currently Sunray Audio is a separate kind of shim emulation layer that just emulates the old Sun Audio API. We're going to replace this in Boomer, and there's some substantial challenges. I think I've already mentioned scalability. One of the other challenges is with the OSS API, you don't have a redirect to tell it what device out in the file system to use. So dev DSP, if you open dev DSP, you need to be able to know which oh, this is a Sunray DTU. I don't really want to play audio on the Sunray server. Fixing that requires virtualized audio, which is actually the next slide after this, if I recall correctly. The other interesting thing is that currently Boomer assumes that we run all audio devices at 48 kilohertz or better, on the assumption that a higher sample rate, if you're mixing everything, you want the best sample rate you can get because you don't want to ever suffer a reduction. You don't want to start your audio mixer at 8 kilohertz and then when you try to play your CD, your audio CD, it sounds like crap. That fixed sample rate gets to be an interesting challenge when you deal with sunrays over wide area networks. 48 kilohertz stereo data, if it's not very compressible, actually chews up a fair amount of bandwidth. I've been having some conversations with the people in the Sunray group to try to figure out the best way to tackle that, and we definitely have some ideas. Virtualized audio. So there's a couple of things here. One is this issue about hot plug, and I remember that example I gave with the voice over IP and you got your movie or your game playing, and you want one on one side, one on the other. Well, there's a whole other kind of user that doesn't do that, and they just want to be able to plug in USB headphones and have it work just like the headphones do on most laptops, where you plug it in, the audio goes here, you take it out, and now it's back over the main speakers. This becomes a policy decision that we need to be able to do. Right now, we don't redirect the link dev no audio. With virtualized audio, I'd like to replace the dev audio link with a real driver that can make real decisions based on user policy. Another good example where right now, or prior to Boomer, the wrong thing happened. If you plug in a USB webcam and it had a microphone, it would replace your dev audio link, and suddenly you lost your output device for the next audio application that played didn't have an output device. So we need to fix that. Another interesting thing has to do with these security zones, trusted labeling. And there's a little bit in here about that, but essentially with virtualized audio, we can be smarter about providing just the access that a labeled zone should have. This zone should be able to play the audio data, but it shouldn't be able to record, except when I explicitly turn it on. Okay. I think I'm going to skip the Nmap support. We're doing more drivers, and then that's it. So, all good?
Yeah, well, thank you, Derek.
Thank you. Thank you. Should I do a little play of the audio test app?